Assalamualaikum and very good evening. Today my team and me, Muhammad Nazif Basri JEFRI, and my matrix number 2010622250 represent about our mini project inverted pendulum system. Next. Okay, for the introduction, we have completed lab 2 where a pole placement controller is applied to control the percentage overshoot and the setting time for the cut inverted pendulum system. However, a significantly anomalous error is found. In order to reduce the error, especially steady state error, the proportional integral directive PID controller must be used to eliminate the error.
Hello, Doctor. I'm Devendren. My metric number is 1910627222, and I'm going to present about the objective and about the methodology. Our objective to design a controller to enhance the cut inverter pendulum system with pole placement. Then, second objective is simulate the PI control of the system using MATLAB Simulink. Third is apply mathematically and programmatically based tuning techniques. And the last, to examine the system performance. Next. And for the Ziegler-Nicholas method, assume K for the steps are assume Ki equals to 0. Then the step 2 the new transfer function is kgc over 1 plus kg plus kc is then obtained. And step 3, using the root Hurwitz method, the table, the value of K creed is obtained. And step 4, values of Ki and Kp are obtained from the K creed value. And the cut inverter pendulum system with pole placement control is an inverter pendulum is a pendulum which has its center of mass above its pivot point. Previously, we were tasked to get the transfer function and state space for the inverted pendulum system. Then we determine the signal flow graph of the system is for simulation using MATLAB and Simulink. Simulation result for the system is a very unstable output graph. There was a steady state error from the output graph. PID controller. For PID is an acronym for the mathematical term proportional, integral, and derivative controller. In this combination, a PID controller is an instrument used in industrial control application which help to regulate temperature, flow pressure, speed, and other process. PID controller use closed-loop feedback to keep the actual output from a process as close to the target or set point output as possible. And next, please. And for the methodology, MATLAB PID tuning. PID tuning is the process of finding the value of proportional, integral, and derivative gain of a PID controller to achieve desired performance and meet design requirements. PID controller tuning may seem simple, but it might be difficult to identify the set of gain that will provide your control system the optimum performance. Traditionally, PID controllers are tuned either manually or use rule-based methods. And also PID can be automatically tuned to achieve the optimal system design and to meet the design requirements. Next, I will pass to Muhammad.
Okay, my name is Muhammad. Okay, for the transfer function of origin system, this is we get from the MATLAB coding, and then we get this transfer function for the angle and displacement. Okay, for we design our design control by the lab 2, and then this is our design control system is percentage 20% of overshoot, and then time settling is 4%, and then we get from the damping ratio formula, and then we get time settling, then we find we can find the omega n, and then we use the formula characteristic equation, and then we input that, then we get our that. But we cannot compare with for other system, but we need to convert that to for other system. Then how we do that? Then we use our desired third pole and the fourth pole, and then we get finally we times the characteristic equation that we find, then we get our desired characteristic equation. And then for the pole placement controller, we need check the controllability. So when we check controllability, that this is formula, and then when the need is equal to 0, then the system is uncontrollable, cannot be controlled. Then we find that the system is equal to 1, so the system is controllable. Then we can proceed our design to find the value of K. To pole placement, we need, and then we finally compare with our design classification with the new K, and then we get finally, and then for the PID controller, we assume that Ki and Kd is equal to 0, and then we times, then we find the closed loop, our closed loop, and this is our closed loop system for function. And then from the new characteristic equation, we input the table, and then find the critical. This is our critical, and then we from the critical you use the formula, and then we get the time critical, and then we input the value that we get from the calculation, then for the table, and then we get finally value for the KP, KI, KP and KID. So we get PI and also PID controller value. Okay, so then we proceed our displacement transfer function. Other so for the second output, we do the same closed loop, and then we finally do table, and then table. Then for demo simulation, okay, for the simulation that this is our pole placement controller, and then the pole placement for displacement position, and then angle position, and then this is the output that we insert, that's PID controller that we get from the calculation, and then this is for the PI controller. Okay, so the output is okay. This is our angle for the PID controller, pole placement and PI controller, and then this is our displacement for the, this is pole placement, PID controller, and then the output from the PI controller.
Okay, next. Okay, we can see over here. Let me introduce myself. I'm Leong. Okay. we can have a look over here. This is for only the plot placement controllers. We can see that this is for displacements. Supposedly, when we have an input for 1, 2, 3, 4, then hence the output should be have same as 1, 1, 2, 3, 4, 1. Okay, but as for only plot placement controller, we face problems that is we have a very serious steady state error. Okay, which is its output usually is around 0.1 something, negative 0.1 something. Okay, so you can see that if using the post placement controllers, it can make the system stable, but then it cannot solve the problem of the steady state error. Okay, next. Why we just now we say it can let the system stable is because as a invented pendulum systems that our mainly focus is focused on the angle. Okay, and then you can see here with the plot placement controller, the degree, the angle, it should be vertical and always keep in zero degree. Okay, and also after we apply the plot placement controller, obviously it successfully keep the systems in keep the angle always in zero. Okay, so okay, so for this one is after we know that with plot placement controller is cannot solve the steady state errors problems, so we try to apply the PI controller because we know that PI controller the main focus is on decrease about the steady state error. Okay, for this ones is setting times is about 5.7 seconds, and also its percentage overshoot is about 4.118%. Okay, so that however we can see that at its final values for whatever input is 1, 2, 3, 4. Okay, eventually their values should be same as their output, and also PI with plot placement controller is successfully solve about the problems of the steady state error. Okay, however, based on lab 2, we have two conditions that we need, two design scenario we need to follow and fulfill, which is we should have the below or equal to 20% overshoot, or and also the setting time should be equal to 4 seconds, okay, or below. But then, like what I said now, the percentage overshoot is different fulfilled already, but then the setting time is about 5.7 seconds. So PI controllers seem like cannot solve the problems, which is the fulfill the design scenario yet. Okay, next. Okay. For this ones is the output, okay, angle output with the PI with plot placement controllers. Obviously, see that with the PIs with plot placement controllers, it can also make about the whole systems maintains the angle at the 0 degree. So we can say that PI with plot placement controller, it can stabilize the systems. However, it cannot fulfill the design scenario. Okay. Forgot to say that it's like for these output diagrams, the setting time is 3.5. It's around 3.5 seconds. So it is fulfill the design scenario, but then the percentage overshoot is highly until 60%. So it's not fulfill our design scenario. Okay. So since the PI cannot solve the problems, then how about we try for PID? Next. Okay. OPID, we can see that for PID, he have the same functions as the PI, but then which is solving which reduce the steady state error, but then he can perform better than PI. Based on the data we obtained that the setting times is about 3.2 somethings, okay, 3.2 seconds. It's around 3.2 seconds, and also the percentage overshoot is about 14.189%. So for displacement output, we can see that the PID is already fulfills our design scenario. Okay. Then next. And then for this ones is the angle output with the PIDs with pole placement controllers. We can see that for the output, actually it don't have the overshoot, but it have the undershoot. And then first thing to say that is for setting times, whatever is the setting times, what kind of input is 1, 2, 3, 4 input, all of them, their setting times is about 3.53. And then is percentage undershoot is about 44.8 something. Okay, 44.8% something. So we can claim that we still fulfills the design scenario is because there is no overshoot but undershoot. Okay. And also the most important for the angle output, we need to check that whether it's always keep at the 0, and also what the values we get is the result for this one final values is 0. So we can say that PID's controllers it can be performs better than PI controller. And then also next, let's see the comparisons. Okay, over comparisons over here, we can see that for the green color one, for green color is the PID with the post placements, and also yellow color is the PI with post placements, and also the green color ones is the post placement. Okay, we can see that if we only have the post placements, it's like what we saw now. Okay, it cannot get the exact output that we want. Okay, but as if we have the PI or PID controllers, both of them can solve about the steady state error. And also we can see the PID, he have the shortest transient response time. Yeah, shortest transient response, which means that his setting times is shorter than the PI controller. So which means that the PIDs with PID controllers, it have better performance compared with PIs in the terms of reducing the transient response. Okay, next. Come to this state, we can see that this comparison is about their angle. Okay, whatever is post placements or PID with pole placements or PI with pole placements, three of them all of them can achieve the same target, which is stabilize the systems. Okay, but then we can still see that the PIDs can have a better performance compared with the PI. Right, because it fulfill our scenario. It don't have overshoot but undershoot. Okay. Yeah. So that's all for our analysis and discussions for our result. So next to the NAZEEF.
In conclusion, the system with merely post placement controller can stabilize the system but with a high magnitude of steady state error. Steady state error can be solved by both PI with pole placement controller and PID with post placement controller to fulfill the design criteria of Lab 2, which is percentage OS below or equally 20% and TS is 40%, or get better performance in terms of reducing transient response. Only PID with pole placement controller can achieve those conditions. Ziegler-Nichols method is important to be used to design in this report, whereas MATLAB Simulink is also important to simulate the performance and obtain the result accurately. That's all from us. Thank you for watching.